Welcome back to simulation and prototyping. This is the third part of a tutorial out of 3 parts where we've built a random wonky kind of star, and then we're dropping that geometry onto a plane and using the Kangaroo 2 solid body simulation to see how that object sits. So if I come back, I can change our object and reset that simulation. We can see the way that it finds a kind of equilibrium between 3 points, between 3 of its legs, as it sits there. And so once you find something that you think is kind of complex enough, I'm going to set our first Kangaroo simulation to false and leave it there. What I want to do now is, as we start the third part of the tutorial, is that we're going to build a second Kangaroo simulation that allows the plane to inflate around the object. And so let's take a look at this now. Let's pull a mesh from this. I think I've done this in a couple of different ways, and it felt like maybe tricked it to work in a couple of different ways as well. Is that let's create a mesh out of our list item, and that's our object that sits there. Let's we're going to have a few extra steps just in the way that we want to define a couple of aspects for some of this geometry. So let's look at our surface. What I don't, let's see, let's use our same thing here. Okay, well, let's start with our plane. So that's the mesh that we're going to inflate against. Let's start with a surface. And this surface, we'll do a surface container. Let's plug in, let's unhide the plane that we defined previously that we're using for our first simulation. Let's set our surface container to be equal to that plane. We can then hide that object again in Rhino. And so let's create a mesh this time. And last time we just defaulted to a mesh. This time I want to be more specific. So let's create a mesh surface. And this is why we had to do this. You can see the surface comes in. Now we can hide our surface from our surface container. But we do want to set the U and the V components. I'm going to pull one of my panels, copy one of my panels from before. And let's set this to be, let's see if we can start with something a little smaller. Maybe let's start with 50. We'll increase it if we don't have the resolution that we want. Let's set this to be both U and V. Okay. We can also, we're getting that pattern so we can hide our first B-rep. And so now we just have our mesh surface here. Let's extract a few elements for the simulation. And this is going to be more about kind of controlling and extracting geometry than anything else. But let's get mesh edges, which is here. So we'll plug in our mesh, and now we can see the grid that's 50 by 50. And we'll be able to pull from this both the naked edges and interior edges. And maybe we'll hold there for a second until it comes time to build some of the things that are going to happen for Kangaroo. Well, let's see. Maybe it's easy to, let's try geometry. So naked edges as we plug this in. So the naked edges are giving us just the edges all the way around. The interior edges are giving us all of the lines that are in the middle. So we're going to use these lines as a way to be the springs of the bouncy solver for the next simulation. So now we have access to those, and that's good. Let's also deconstruct our mesh because we want to get the vertices. And so let's do deconstruct mesh. We'll plug in our mesh to this. And now we can see we get all of the vertices that are there. And that's going to be another aspect to something that we're going to have to both, this is what we're going to, those vertices we'll use to add the weight, and we're also going to use them for the collision. And let's do, well, maybe let's plug in a few of these things and start building this. So I want to copy, well, let's just build it. So let's create our merge. Let's add our bouncy solver. And let's add our show. So we know that the merge is going to be our goal objects. We want to flatten that down. We want to have our iterations set to 50. We want our Boolean toggle. We can leave it set to false for now. And we also want a button so we can reset. So those are all the key elements that we need to set up our bouncy solver. What we want to show is going to be our mesh. So here's our mesh into our show. Our show goes into our merge. And let's see, let's add our loads next. And so this is going to be the goals, and there'll be point loads. So we already know that from our point loads, we can pull our vertices. So this will come into our merge, and our force vector will also be Z this time, but it'll be positive. And let's make it just positive 0.1. So we have that all of those points will be pushed up from the bottom with a force of 0.1. And again, we may change a few of these values as we go and as we work through the simulation. Let's now set the line lengths, and this is going to be under goals line, and we'll use line length of the line as the next key element of our simulation. We just want to control how kind of flexible each of those lines are. And so the lines that we're going to use are both the naked edges, and we'll also add the interior edges, holding down Shift into both of those lines. And the length, we're going to leave alone. And the strength, let's set to be 100. This will then plug into our merge. And okay, let's see what's next. So now we need to collide it's a few steps. So let's go all the way back to the beginning. So from our mesh, which we have over here, maybe I can hide, let's see, maybe let's hide, see if we can hide all of these things. Leave our bouncy solver on, which I guess gives us all of those points. So from our mesh, what we need to do is to create our solid object. And so let's get our face boundaries. This is going to convert all mesh faces to polylines. So now that's at this element. Now we can see that these are those edges. Let's create this to surfaces and join brep. The difficulty here, and the reason why we're doing this, is that to go from this was a brep, we had to convert it into a mesh in order to simulate it. Here we have a mesh. What we basically have to do now is to convert this back into a brep for the solid body simulation. So we're going to take our face boundaries, then we're going to make boundary surfaces from those. Right now we have a whole series of trimmed surfaces. Now we'll brep join these. So what we end up with is now a brep. And the reason why, again, that we had to do that, why we can't go back to our earlier brep, is that this was a mesh from the simulation, and we just, through these couple of steps, changed this mesh into a brep. And so now that we have that, we can see, let's see, make a quick panel. Breps coming out of this. We can see open brep, trimmed surface, open brep, trimmed surfaces. So it's a whole collection of different elements from that. Let's cap our holes. And for this, we're going to use cap holes X, cap as many holes as possible in a brep. I wonder, okay, so that's under surfaces. Cap hole X. I was afraid it was coming from a plugin. So we'll plug in our breps into the brep. And then let's join brep again. Brep to brep. Check what this is. So now we can see we get a whole series of closed breps. That looks a lot better. And from that closed brep, let's see if that works. Let's plug in our solid point collide. And so let's just move, just because I want these things to kind of line up vertically through here. To make the understanding of the Kangaroo simulation a little bit easier next time when you open your file, is that so this brep, what we're going to do is go to Kangaroo 2, and what we want are solid point collide. This is under goals collide. And there's a solid point collide. And the reason why we're doing this is that our solid is our object. Our points are going to be all of those points from the flat mesh. And we'll be able to look at how those things are interacting with one another. So from our brep, that's going to be our solid. Our points are going to be the vertices from our mesh. And the strength, I had this set to a very high number. Let's see what makes sense as we do this, I want to say I had it set to 10,000. We'll see if that's right in a second. So we'll plug this into our merge. And then we need one more element, which are some anchors. And the anchors, the same thing, we've done this before in a previous tutorial. What we want to do is we're going to kind of screen out some elements that we don't want. So from our mesh, let's see what we get here. Where is this coming from? So let's deconstruct mesh. And that mesh is going to be, should be that mesh surface. Although we already had a deconstruct mesh and the vertices. Yeah, actually, let's see. Seems like maybe I had an extra step before. We'll see if this makes sense or not. But what we want to do is partition this list. We'll partition the list of vertices. And what we want to do is to pull, we basically want to add 1 to the size from our value up here on the top. And so let's do that with an expression. And I prefer to do this using the expression. Just again, like I said, sometimes we come back to our Grasshopper files. And if it's been a while, you may not. We can always add a +1, but it's embedded within there. So I much prefer to use an expression. And so we can get rid of the second one. We need to name it variable X. Double click, we'll change this. It's just going to simply be X +1. And the number that it's going to come from is our panel up here on the top, which is setting the number of divisions of our mesh. So we have that. We'll plug this in for the size. And so what we're getting, maybe we can see it with a panel. So our mesh, so just our vertices alone, as we plug this into a panel, what we should be getting is 50. All right, so what we're getting is a list without any divisions. So by partitioning the list, what we're going to do is to basically break our list into the row of points. And that's what we want to use to fix our mesh. Basically, we want to use the points along the 4 edges. That's what we're trying to get to. So let's do list item. We're going to do this twice. Getting a little messy down here. Copy this twice. And so the first list item, let's pull our list. And this is a nice trick with our list item, is that we can add either to the bottom, which is +1, or to the top, which is -1. And so what we want is the first row of points and the last row of points. And so let's look at this. Maybe I can do a point container. We can see what these look like. So here is the -1. Here's the +1. And this is because we have wrap. on. If we turn wrap to false, don't believe, see, it doesn't give us the -1 anymore. And so we need the list to wrap in order to be able to access that portion of the list. So in this case, we have the first and last row in the X direction. And so we're going to create another merge to just begin to merge all of these. And so what we need to do is now get the other two edges to be able to constrain this object. The way that we're going to do that is the same thing. We're going to get the -1. And from those chunks, what we're going to do is flip the matrix. And again, the way that I typically describe this, flipping the matrix is like taking a spreadsheet and changing something that was rows into columns or something that was columns into rows. So as I take those chunks and now I plug this into the list, what we should get is the first row of points in the Y direction and the last row of points in the Y direction. So now we can merge all of these points and flatten them down. And what we should have now is the complete perimeter of all of those points. We structured this in an associative way so that if we change the number of points or the number of divisions between the U and the V in our mesh, this will also change. And so that's driven by that 50 that's above. It just allows us to sort this data and go from there. So the last thing that we'll do is plug these in and create these as anchors. So it's a little bit of setup. I want to move these over. Like I said, I've been trying to get these elements to line up so that now our Kangaroo elements will all line up. And so under goals for points, we want to grab the anchor. Those are our points. The strength can be 100. So we can copy this panel, plug that in, and then this should be the last element that we plug into our merge. We should be able to hide these. Hide anything else that leads up to that, and we'll see if this works. So generally, what we see happening here are the elements that lead up to the simulation, the key elements, which I could group here for the Kangaroo simulation, and then the simulation here off to the side. So let's do the same thing that we've been doing, which is pull for the outputs of that. We'll create geometry. I think this hasn't run yet, so there's probably nothing there. So let's hope, let's change this, let's turn this on. And what you should start to see is the mesh being inflated, what I would say is inflated from the bottom and starting to become a pillow. The points on the mesh are intersecting with the object or with the edges of our solid element. So I'm going to turn this back to false. And let's take a closer look. And so if we look from the bottom, it looks like our element, we can always zoom selected. It looks like our element is piercing through the mesh. The reason for this is because we can increase our resolution. And it just seems like, at least in this case, one of these points of this mesh didn't intersect properly. So let's try increasing our density of our mesh. And so I'm going to go from 50, and I said this when I made it that to 50, it was like to try and go as low as possible. But if you really want to be specific, maybe we don't want that element puncturing through the surface. So let's go to 75. Your computer may not be too happy. I say that. Now is probably a good time to save. Before you do that, okay, that is set to false, so that's good. So let's save. I already have this set as starfish tutorial. I'll save rhino. I'll save the grasshopper. So we can reset. And then we can turn false to true. And we should see this beginning to inflate. Mine is at least a little bit slower than it was. This simulation does take more memory and more time than the previous simulation. And we could also change our star object because maybe it's just too pointy, or maybe where it fell isn't perfect. But we'll let this run. And this is the 50 iterations. Maybe we can turn that back down. Maybe we can try 10. We can also try changing some of these other values. But for now, this should be working for you. I'm going to see if I can set that to false. Okay, so we can take a closer look. I tend to change it to false if I want to change anything. I don't want this calculating anything in the background as I try and change it. Okay, so the last thing that we could do for any of this is that I want to clean the tree, and I want to put this into, let's see what I was doing here. Right, so same as before. Let's take this geometry, see what it is. We can see we get a bunch of nulls, we get a bunch of things. Let's clean this tree. Let's see what we need. How many are coming out of this? There's a mesh, there's a whole bunch of lines. So let's do list item. From the tree, I'm hoping let's try 0. Hoping the first element is our mesh. So there it is. That looks good. Let's see if we can contour this. So under curves, analysis. Maybe that's not the right place, but let's try a contour. So it does allow us to contour a mesh. Here's our shape. Our direction should be Z. Distance, maybe 2. So we can increase our contours. 0.2. So that looks pretty good. And so we have our list item. We could just do a couple of representational things. So let's copy our custom preview. And let's make our mesh a more neutral color. Light gray. And let's make our did copy that. Now we can also make our contour lines. Black. So now we get a nice representation of our object as it's fallen and as it's sitting within the contours. We want to increase those. Once more. Some additional contours. And we've got all of those things. So this is looking good. Now I'd say maybe it's just worth first saving so you don't lose these. Let's look if there's anything that we want to clean up as we do this. But our second grasshopper, sorry, our second kangaroo is there. Let's pull our second simulation toggles all the way over to the beginning. And so this will allow us, without having to scroll too much on our screens within the canvas, to run a couple of versions of this and see if it works. So what I would do is make sure both of your kangaroos are set to false. We can reset both of them. So we have our plane. Let's change our first element. My whole system is running a little slow now, given that I'm recording the screen and other things are happening in the background. But I would change your seed value to an element. Let's see how that will fall. This is our first simulation. So let's set this to true. Should drop. I'm worried I have some, okay, here it goes. It just started dropping. I was worried I had something hidden that shouldn't be hidden. So it just hit the plane. We'll let it bounce and find its equilibrium. And again, remember, it's the load on that is just from the centroid, pulling it straight down. So it will find the first 3 points of the object that hits the surface, and it'll continue pulling it down. And that's why we're going to set this to false once it finds its equilibrium, which that looks pretty good. So we'll set this to false. We'll wait for that to register. So now that's false. And so now let's inflate our ground plane around it. So we'll change the second one to true. And now because we have the contour lines also set, we can see the contour lines being created as the surface is inflating. And if you want more inflation or less inflation, you can change the vertical positive Z load on all of the points. That will allow it to stretch more or less. You can also change the strength of the springs of the lines as well. And so here, let's see, in other instances, I think my plane wasn't so large. So what's happening now is that because the plane is so large, we're going from 0 to a kind of large hump to where the object is. If you want to make your plane a little bit smaller, you won't end up with this quite the same way. So that seems like it's kind of finished. I want to set this to false. And then, okay, so that's set to false. I want to see how quickly now I could change. I think I just unhide that surface and select that surface. And maybe I'll just scale 1D. Maybe make it about 50% of what it was. In both directions. And I'll just move it. Like I said, there's a lot going on my computer, probably on yours as well. So let's just get that plane a little bit smaller. And as we move it, you'll get a sense when we run this simulation, the way that it's going to inflate under your object is going to be different because of that size. My computer's not happy right now. Just give it a second. Okay. It looks like I don't know what that is right there, but let's hide. Oh, not lock. That's not what I meant to do. Okay, so we hid that. Let's see what happens if we reset with the button. Okay, so that artifact just went away. Now let's inflate our ground plane. We should see more kind of swelling of the surface under the object now, because remember, it's only constrained at the edges and at those points that are hitting that surface. And so we're getting a bit of a different result now because of that overall size. You can set this to true. And the last thing that I'll do for you is just to show you what happens if I change the load or spring strength. You can see it's still resolving the inflation. Looks okay, and now it just went to false. So if you want to see more extreme inflation, the two places that I would look at that would be in the strength. We'll leave the anchors alone. We'll leave the collide alone. This would be in the strength of the line or in the force of the vector. And so if we went from 0.1 in the unit z direction, let me try 0.5, which is a substantial increase. Let's reset it. And we'll turn this to true. So now the topography is much taller than it was a second ago, which makes sense. We're applying much more vertical load on all of those points. We'll wait for it to settle down. We'll set this to false, and then we'll take one last look. All right, that's been set to false. If we just look overall, We can see our key elements here, our geometry, the random portion of our geometry, our first kangaroo, and our second kangaroo. So now what we end up with is nice topography, our object kind of deeply embedded within that. We can see it from the bottom. We can see it's not perfect in terms of that. If we really wanted to look at that, I think we could again increase our mesh size or increase our mesh subdivision to make sure that more of those points, or sorry, in that case, it's the edges, are catching the lines as they move through there. But from the top, we get a pretty good representation of what this object would look like as it would fall, as it would come to rest, and as it would be there. So I hope this was fun. Again, you may or may not be creating physical models or digital models like this. That's okay. There's 3 different parts that come together. A simple way to generate some form, given the random numbers, looking at solid body collisions, and then looking at how to inflate one object against another object. So I think that I think these should be helpful. I hope you enjoyed this. I hope it's helpful. Please share your comments. Please subscribe to this channel if you found this helpful. Thanks.